Everyone, so we've looked at magnetic flux, and we've watched how magnetic flux changing induces currents in conductors, but we need to go a little bit further with that, and this is what Faraday looked into, was that what causes a current in a conductor? Well, the answer to that must be voltage. Voltages drive charges, they create electric fields, and make charges move from high to low potential. So when we have induced currents because of these changing magnetic fluxes, that means there must be an induced EMF or an induced voltage from this changing magnetic field. So Faraday simply said this, that an induced EMF in a conductor is equal to the change in magnetic flux, and that change in magnetic flux will drive current through the conductor specified by the direction from lengths. So the direction that we talked about where the magnetic inertia wants to maintain the flux that it was used to having. So this is Faraday's equation. Faraday's equation says that the induced EMF in the loop, or the induced voltage in a conductor, is equal to the change in magnetic flux over time. Now if there's multiple loops, we're going to have to put a large N there to indicate the number of loops with the magnetic flux that is changing. So this is how you'll see it written. N d flux dt is the induced EMF in a conductor. On the equation sheet you may see it written as negative N d flux dt. I would rather you do the absolute value to figure out what the induced voltage should be, and then use Lenz's law to tell me the direction of the induced current. So let's do some examples to show you how Faraday's law can be applied. So let's say we've got this example. We've got a magnet, and that magnet is moving towards a coil. The coil has 100 loops or turns in the solenoid. So the question is, what is the induced EMF inside that setup? Faraday's law says that the induced EMF is N d flux dt. So we already know one thing. We know the number of turns is 100 loop. Let's talk about the changing flux. For flux, remember we need magnetic field times the area. So in this case, the area is the area of a loop, so I would need to know the radius. So I've got a area that is not changing, so that's a constant. So what must be changing for our d flux must be my magnetic field. So my magnetic field is going to go from 0 when the magnet is very, very far away to a value of 2.3 Teslas. So it's a very, very strong magnet that's moving into this coil. Let's say it does that in a time of 0.75 seconds. So I know the time, I know the change in magnetic field, so let's plug in the values that we do know. So plugging in our values here, we can see we have 100 turns. Our magnetic field went from 0 to 2.3 Teslas. The area was pi r squared since it is a circle, and we've got a 0.75 seconds as the time change for how quickly that magnet went from being far away from the loop to fully into the loop. Doing that, you get 60 volts of induced EMF. And one thing we could ask then, let's say that the resistance of the loop is 10 ohms. So the question would be then, how much current have we induced? Well, we know our voltage and we know our resistance, so that means I'm going to pull about 6 amps of current just by sending a magnet from far away straight through that loop. Now the next thing we need to know is the direction. Where is that induced current going? Is it going clockwise, counterclockwise? So remember, the magnetic field is going through the loop here, and the magnetic field is increasing. That means the loop is going to resist by sending its own magnetic field back out. So to do that, you would have to send current in this direction. Put your thumb in the direction of current, and it's going to throw a magnetic field back at the magnet, trying to resist that change in flux. And now we know how much it's inducing a 60 volt EMF, which is driving 6 amps of current through that loop. But what if it's not that straightforward? So let's say we've got this setup. We've got this semicircular loop that's in a magnetic field, and the magnetic field is given by an equation like this: 8t squared plus 4t plus 6. The question is, what is the induced EMF in this loop? So the induced EMF is N times d flux dt. The nice thing is that there's only one piece of wire here, so the N is 1. So that means I just have to do d flux dt. Well, flux, magnetic field times area, and the area is not changing in this loop, so the magnetic field must be changing. So we're going to have to take the derivative of dB dt and multiply by the area. The area is going to be pi r squared, but it's going to be half of that since we're just dealing with a semicircular loop. So taking the derivative of the magnetic field, I'm getting, gives me this, 16t plus 4 times pi r squared over 2. Now, we'd have to ask ourselves, with a changing magnetic field like this, what is the voltage at a certain amount of time? So what happens at, say, 10 seconds? Because at 0 seconds, I can tell you the magnetic field strength was 6 Teslas, and as time went on, the magnetic field was increasing, meaning there got more and more magnetic field strength as time went on, and as the magnetic field was increasing, that means the magnetic flux was increasing, and it's inducing a voltage at the 10-second mark of around 41 volts. So we have 41 volts that's induced in that loop. The question is, where is the current going? Well, if there's more dots, more magnetic field coming out of the page, that means that the wire itself is going to try and send magnetic field back into the page to resist this increase in magnetic field. And if that's the case, to throw field into the page, it's going to send current in this direction. I do know that there's a 2 amp or 2 ohm resistance down here, and I know the 41 volts, so I can figure out that I've got 20 amps heading back across the battery in the wrong direction. So what's going to happen here is that you're going to recharge the battery just by putting that loop in a changing magnetic field. Since the potential difference is induced in the loop, that must mean that there's an electric field that sets up. Electric fields, remember, push charges, so as magnetic fields are changing, you get an electric field to grow and push charges through that wire. The question that someone could ask is, what if you had a conductor inside this magnetic field and outside this magnetic field? How would you find the electric field for conductors that are within these two radiuses? So let's start with a loop that is little r, and let's say that we have a magnetic field, like we said here, into the page, and the magnetic field is increasing into the page. So we're getting stronger and stronger magnetic field as time goes on. So let's first use Lenz's law to figure out which direction the charges want to move. We know that those charges are going to want to resist that increase in field, and they're going to send their own magnetic flux in the opposite direction, so there must be a current in this direction. So there must be an electric field that's pushing charges in the same direction. Electric field that is going to push those charges from a high to low voltage. We know that induced EMF is negative d flux dt, and we know that voltage back from electricity is the integral of E dot dl. So what we can do is we can set both of those voltages equal to each other and give us one long equation to solve for the electric field. And there you go. So since the induced EMF creates these electric fields, that little circle there is the integral around a closed loop. This is how we can find our voltage for the induced conductor. It's equal to the negative change in magnetic flux over time. Remembering that magnetic flux is B dot dA over dt. If I want to solve for the electric field around my interior loop, I can say the electric field will be constant around that. So let's solve for the electric field inside that small loop that I made in the beginning. So around that loop, I can say the electric field will be the same strength all the way around, and I just have to integrate dl. dl will be the distance around that conductor, which will be 2 pi little r, so the circumference around there. On the other side, the magnetic field times area, the area of that loop is going to stay the same. The magnetic flux is changing with time. The magnetic field strength is changing as time goes on. So the area of that conductor loop, pi little r squared, and some of the things can cancel for us. And if I want to solve for the electric field strength, the electric field inside this conductor is equal to negative little r over 2 times the rate of change of magnetic field over time. So here's the electric field for that interior loop as the magnetic field is increasing into the page. If we're looking at a loop outside of this magnetic field strength, so if little r now is the distance to my conductor that is outside this circular magnetic field, again, magnetic field is increasing into the page. The loop is going to send magnetic field back out of the page to resist that and still send current in the clockwise direction. But now we're encompassing more and more of the magnetic field with a bigger area. So same setup as before, that the induced EMF will be the rate of change of magnetic flux over time, and that voltage equals electric field times distance. Again, integrating dl. dl is just going to give you the circumference of our conductor. So again, that's still 2 pi little r because the conductor is r distance away from the center. And again, we have a change in magnetic field over time, but this time the area that has the flux changing is just pi big R squared. Now have a conductor that is outside of the entire magnetic field area. So only a few things can cancel this time. Really just the pi's can go away. So the electric field outside this magnetic field area is negative R squared over 2 little r multiplied by the rate of change of magnetic field with time. So one more thing they may ask you is to graph the induced voltage as you pull a loop through a magnetic field. So let's say we've got this square loop and it's moving at a steady speed as it passes in and out of a magnetic field. What we want to do is discuss the induced EMF at these various locations. We'll call this location A, B as you're entering the field, C as you're in the middle, D as you're exiting the field, and E as you are leaving the field completely. So in the beginning here, there is no flux. There's no magnetic field going through the loop. Change in flux is 0. So based on Faraday's law, the induced EMF must be 0. So for the first segment here, there is no voltage. Okay, what happens when the loop starts to move? As the loop starts to enter the magnetic field, there are now X's into the page, so the loop's going to throw dots out of the page to try and maintain the flux, which means there's going to be current heading in this direction. There's going to be an increase in the flux as the loop enters, and since this is negative d flux dt, as flux increases, that means the voltage will have a negative potential as it enters section B. Let's look at it when it gets to section C. There is magnetic flux now, but the flux isn't changing. So with a change in flux equal to 0, that means there's no induced voltage again. The current stops in the loop and it's used to the magnetic flux now. So when we get over to section C, we're back to 0 voltage. Watch what happens when we get to section D. We are leaving the magnetic field, and now the loop is used to the magnetic field. It wants to maintain the magnetic field. So it's going to throw its own magnetic field back into the page. And to do that, you've got to send current in the opposite direction. So according to our rules, our change in flux is decreasing. And if we have a decrease in our change in flux, since voltage is negative d flux dt, we're going to have a positive increase in voltage. So the voltage is going to be higher now. And then once the loop finally exits at location E, the magnetic flux is all gone. It's now used to not having flux anymore, so the voltage, the induced voltage, drops back to 0. So they may ask you to graph this, and looking at a induced voltage graph, you should be able to figure out what the loop is actually doing, when the magnetic flux is changing, and how quickly.